Agni MIRV capability, credible, survivable second strike posture. In nuclear deterrence, credibility rests on two pillars: the ability to absorb a first blow and the certainty of a punishing reply. Multiple independently targetable reentry vehicles, MIRVs, on an Agni-class missile strengthen both pillars at once. Instead of a single warhead on a single trajectory, a MIRV bus carries several warheads under one booster, releases them on distinct paths in space, and steers each toward a different aim point. That turns one launch into several simultaneous dilemmas for an adversary's defenses and compresses the time in which they must decide, track, and attempt to intercept. The hardware logic is straightforward. A high-energy, solid-fuel Agni booster lifts a post-boost vehicle, often called a bus, above the atmosphere. There, free of drag, the bus uses small thrusters and precision guidance to reorient and release reentry vehicles one after another, each with its own trajectory and timing. In the seconds between separations, the bus can alter velocity and attitude so the warheads spread laterally and in range. Arriving on multiple azimuths and at staggered times, defensive systems that expect a single inbound track now face a cluster problem: which to engage first, where to commit finite interceptors, and how to distinguish real RVs from any penetration aids that may accompany them. Survivability improves before launch as well as after. Solid-fuel Agni variants are road or rail mobile, dispersing across hides, tunnels, and prepared sites to complicate preemptive strikes. Mobility plus shoot and scoot doctrine shortens the window between detection and launch, and hardened, redundant command links preserve positive control without creating single points of failure. When a launcher does fire, a single MIRV round can service several high-value aim points that would otherwise require multiple single warhead missiles, conserving inventory and reducing exposure to counter-force attacks on reserves. Accuracy and guidance are the quiet enablers. An inertial navigation system refined by stellar or satellite updates drives the bus to the correct release basket. Precise attitude control and timing ensure that dispersion on the ground matches the plan. The reentry vehicles themselves are largely ballistic in the terminal phase, riding extreme speeds through the atmosphere to minimize the defender's engagement time. Even modest terminal shaping of RVs can tweak footprints and heating profiles, complicating discrimination by radar. The result is a package in which geometry, speed, and timing, not just yield, do much of the deterrent work. Penetration against layered defenses is a design goal, not an afterthought. MIRV saturation lowers the defender's per-target interceptor density. Decoys or chaff can seed the defender's radar picture, and varied trajectories, some slightly depressed, others higher, force multiple fire control solutions. From the defender's perspective, the cost curve tilts badly. Each RV demands an interceptor or two, and intercept windows can overlap if arrivals are staggered cleverly. Even a capable defense risks leakage when faced with a well-planned MIRV profile, which is precisely what second strike credibility seeks to ensure. Command and control keeps deterrence stable. A robust, redundant chain of custody over warheads and launch authorization is paired with tested drills for dispersal, communication checks, and pre-delegation protocols appropriate to national doctrine. The purpose is paradoxical but vital. Make it hard to fire accidentally, impossible to fire unlawfully, and certain to fire when lawfully ordered after absorbing an attack. Exercises that validate communication survivability under electronic attack and physical disruption are as important as range trials of the missile itself. Integration with the broader triad increases resilience. Land-based MIRVed Agni systems complement sea-based ballistic missiles on SSBNs, which provide stealth and constant patrol, and air-launched vectors that add flexibility and signaling options. Together, they prevent an adversary from betting on a single decapitating strike. At least one leg will ride out the first blow and hold targets at risk. Within that mix, MIRV capability multiplies the land leg's efficiency. Fewer launchers can hold more discrete aim points, spread across leadership, command, air defense, and infrastructure nodes. arms control literacy and doctrine shape use. Credible minimum deterrence is about assured retaliation, not warfighting. MERV does not seek to blur thresholds. It seeks to guarantee that any nuclear use against India is answered decisively. Declaratory policy, restrained testing, and secure operations reduce the risk of accidental escalation while still signaling that counterforce fantasies are futile. Penetration aids and MERV bus logic remain opaque by design, preserving uncertainty for an adversary while staying within national commitments. What changes for strategic planners is options and confidence. With MERV, target sets can be covered with fewer launches. Routing can exploit geography and defensive gaps, and reserve forces can be managed more prudently over a crisis timeline. For an adversary, the presence of MERVed assets complicates first strike calculations and interceptor stockpiles, increasing the incentive to avoid nuclear adventurism. MERV on an Agni-class missile turns assured retaliation from a promise into a physics-backed problem an opponent cannot solve cheaply or quickly. It deepens survivability through mobility and dispersion, multiplies effect through multiple aim points per launch, and strengthens the credibility of India's second strike posture without changing its restrained doctrine. For clear explainers on MERV technology, triad survivability, and India's evolving deterrence architecture, visit globalinfoveda.com.
XR-SAM, India's long-range shield between S-400 and MR-SAM. India's air defense map has two strong anchors today: the very long-range S-400 batteries and the mid-tier MR-SAM network that guards cities, bases, and fleets. The gap between them is where the XR-SAM concept lives, a domestically developed long-range surface-to-air system designed to extend India's defensive reach, thin out raids before they reach terminal layers, and give commanders more shots across more sky with Indian control over software, seekers, and supply. Think of the problem first. Modern air threats arrive as mixed packages: high-flying bombers launching standoff weapons, fighters skirting radar at low level, sea-skimming missiles riding the horizon, and ballistic or quasi-ballistic weapons diving fast. If the first hard intercept happens very close to the target, even a successful kill can leave debris and missed leakers. A long-range Indian-owned layer adds an earlier engagement window, nudging the whole air defense fight outward. XR-SAM's architecture is built around three ideas: range, discrimination, and resilience. Range comes from a high-energy missile stack, boost, sustain, and terminal control that can prosecute aerodynamic targets at several hundred kilometers, with a second family scaled for medium-long shots and a third for close-in endgame. Discrimination comes from multi-mode seekers that can pair an active radar seeker with a secondary mode, home on jam or passive cues, so that jamming turns into a targeting aid rather than a shield. Resilience comes from distributed launchers and multiple radars, surveillance to sweep wide, engagement radars to lock and guide, and passive EO sensors to cross-check. So a single node failure doesn't blind the battery. At the heart is a phased array radar suite tuned for long-range surveillance, missile guidance, and clutter rejection over land and sea. Low side lobe designs, electronic countermeasures, and frequency agility keep track steady when an adversary tries to blind or spoof the system. For sea skimmers and terrain-masked flyers, high elevation masts and netted sensors extend the radar horizon. For high-altitude threats, precise track-while scan enables multiple simultaneous engagements without losing picture on the rest of the sky. Engagement logic follows layered doctrine. The battery creates no-go volumes around high-value areas and corridors that hostile aircraft must avoid or accept attrition. A long-stick interceptor takes the first shot at bomber and fighter tracks before they can launch, or at least far enough that their standoff weapons lose ideal release geometry. A second wave of interceptors handles cruise missiles and difficult crossers. If a ballistic or quasi-ballistic threat appears, specialized versions with high-G endgame control and smart fuse logic aim for a body or fragment cloud kill well forward of the defended asset, handing any leakers to lower tiers. Networking is where the system earns its place. XR-SAM batteries are designed to plug into India's integrated air command and control system so that fighters, AEW&C, ground radars, and naval sensors share a common air picture. Cooperative engagement allows a launcher to fire on a track provided by a distant radar, while data links keep mid-course updates flowing until the seeker takes over in the terminal phase. This turns the defense from a collection of point bubbles into a wide, stitched canopy where any sensor can cue any shooter that has the geometry. Mobility and survivability are operational requirements, not afterthoughts. Road mobile launchers disperse quickly after firing. Radars use emission control profiles and decoys to complicate anti-radiation missile targeting. Power and communications have redundancies, including fiber, radio relays, and satellite backups. Shoot and scoot drills and camouflage discipline keep a battery alive against pre-planned strikes, while hardened shelters and rapid mass lowering reduce setup and teardown times. Indigenization is a strategic advantage baked into the design. Domestic seekers, programmable fuses, guidance computers, airframes, canisters, and ground vehicles reduce exposure to foreign supply shocks and allow rapid software updates as adversary jammers and tactics evolve. Commonality with existing Indian missiles, propellants, electronics, and canister standards simplifies production lines and spares. On a commander's map, XR-SAM changes geometry. Fewer enemy aircraft can reach ideal launch points. Cruise missile salvos face attrition early, high-value ISR platforms are pushed back, and friendly fighters can operate with a deeper protective umbrella, conserving their own long-range weapons for offense. Over-water coastal XR-SAM arcs pair with shipborne MR-SAM and long-range ship missiles to build overlapping bubbles that protect ports and surface groups as they sortie. Limits and counters are part of the calculus. Long shots mean long timelines. Tracks must be maintained through evasive maneuvers and jamming. Saturation attacks test magazine depth and reload drills. Low observable targets compress detection range. The answer is doctrine as much as hardware. Stack layers, net radars, pre-planned shot discipline, and train mixed fighter SAM tactics so that each domain covers the other's blind spots. The strategic payoff is an Indian-owned long-range shield that sits between imported very long-range assets and domestic medium-range systems, turning the air defense fight into a deeper, more flexible game. It buys time and distance for decision-makers, raises the cost of coercion from the air, and strengthens deterrence without broadcasting vulnerability to supply chains beyond India's control. For deep dives on India's air defense network, next-gen seekers, and layered engagement doctrine, visit globalinfoveda.com.
Hypersonic cruise pathway, from technology demo to fielded capability. Hypersonic cruise flight is less a single breakthrough and more a stack of hard problems solved in sequence. Start a supersonic combustor, keep it lit, steer precisely at Mach 5+, and manufacture the airframe at scale. India's pathway runs from demonstrators that prove physics to an operational missile that commanders can schedule on a tasking board. This is the detailed explanation of what must happen between a technology demo and a fielded hypersonic cruise capability. It begins with propulsion. A scramjet needs air compressed by speed itself, no rotating compressor. So the vehicle must be boosted to supersonic, hypersonic conditions before the engine can even try to burn. A solid rocket or liquid booster lights, accelerates, and then hands airflow to the scramjet isolator and combustor. The first milestones are ignition and stable combustion across a range of Mach numbers, angles of attack, and inlet pressures. Engineers iterate inlet geometry, fuel injection, often gaseous kerosene-based with pilot flames, flame-holding cavities, and thermal liners until the engine lights fast, stays lit through shocks and maneuvers, and shuts down safely on command. The structure must survive heat and stress. At Mach 5 to 7, skin temperatures soar, leading edges and inlets see brutal heating, and pressure loads vary with every gust and bank. That drives materials choices, high-temperature alloys, C6 composites, and active or passive cooling in hotspots. Panel joins, control surface bearings, and sensor windows need to work after minutes of thermal soak, not just seconds in a wind tunnel. Ground rigs and plasma arcs test coupons. High-enthalpy tunnel runs validate heating models. Then flight data refines the thermal map so margins are real, not guessed. Guidance, navigation, and control turn speed into accuracy. Inertial measurement units drift quickly at hypersonic timelines unless aided. Star satellite fixes help mid-course, while terrain or sea matching can refine terminal aim over land and coast. Control comes from body flaps, canards, or fluidic jet interaction in the inlet afterbody. Algorithms must reject sensor noise from shock buffet and keep the vehicle on a narrow energy band so the scramjet neither starves nor chokes. The payoff is repeatability, a vehicle that holds commanded altitude, range, and cross-range while still executing terminal maneuvers to complicate interception. Test campaigns move from clean demos to operational realism. Early flights prove boost transition, scramjet cruise, and telemetry. Next waves add guidance waypoints, bank-to-turn logic, terminal dives or cross-range jinx, and seeker windows for future variants. Range safety, ship tracks, and chase aircraft collect data. Each shot updates the combustor map, the thermal life model, and the control laws. Reliability scoring evolves from engine lit to met target window in adverse winds with margin. Warhead and effects are sized for the envelope. Hypersonic speed provides kinetic energy. A compact unitary warhead with smart fusing can finish ships, harden nodes, or radar faces without a huge payload. For maritime targets, sea skimming is less practical at sustained hypersonic speeds. A mid-altitude approach with a steep terminal dive balances survivability and accuracy. Overland, terrain masking at hypersonic pace is limited. Instead, altitude control, cross-range, and timing craft a flight path that avoids dense defenses and arrives from non-obvious bearings. Networking turns a fast missile into a smart one. Launch on remote from patrol aircraft, ships, or satellites provides the initial track. Mid-course updates via directional links can refine the path if the target moves. Because hypersonic windows are short, Q quality matters more than for subsonic cruise. The kill chain must deliver fresh, precise coordinates just in time, not too early. Where updates are impossible, scene match or terminal seekers, RFIR, give last-mile assurance without broadcasting the vehicle's position. Counters exist and shape doctrine. Defenders are experimenting with wide-area infrared tracking, high-power radars at unusual elevation angles, and intersectors optimized for high closing speed endgames. The response is speed plus unpredictability. Vary altitude, bank to change heating signatures, arrive in coordinated packages with decoys and standoff shooters, and keep the launch platform outside adversary threat rings. Hypersonic cruise does not make forces invincible. It makes specific time-critical targets harder to defend when timing matters most. Industrialization is the leap from can fly to can field. Scramjet combustors and inlets must be produced with tight tolerances. Heat-resistant materials need reliable domestic supply. Canisters, boosters, and ground support must be standardized, and depot-level repair must be defined so airframes can be turned around after real thermal cycles. Software is a product. Combustor control maps, guidance laws, and seeker code need version control, cyber hardening, and rapid update pipelines as data arrives from tests. Integration with India's force structure decides value. Air launch extends reach and complicates defenses. Ship and coastal batteries provide persistent maritime pressure. Road mobile launchers put inland nodes at risk without exposing aircraft. Pairing with space-based surveillance, maritime patrol aircraft, and AEW&C creates a find-fix-finish loop fast enough to exploit hypersonic speed. Doctrine will reserve hypersonic cruise for high-value, time-sensitive targets where minutes change outcomes. Subsonic cruise and ballistic options carry the routine load. The destination is an operational weapon that commanders trust. Predictable ignition, stable cruise, accurate terminal, and sustainable production. Getting there is an engineering marathon. Propulsion, heat, control, guidance, testing, and manufacturing. Run in parallel with a kill chain that can feed it credible targets. For deep dives on scramjets, thermal protection, and India's roadmap from demo flights to deployable hypersonic cruise, visit globalinfoveda.com. Astra Mark II and Mark III, extending IAF's beyond visual range edge. Air combat is decided long before pilots see each other. India's Astra line is built for that invisible fight, taking the first clean shot, holding guidance through countermeasures, and forcing opponents to maneuver on India's terms. As Mk2 and Mk3 mature, they extend the Indian Air Force's beyond visual range edge, from a national lab curiosity to a family of frontline weapons optimized for South Asian airspace and the wider Indo-Pacific. Think in terms of no-escape zones, not headline ranges. Astra Mark I proved the baseline, a solid high-G missile with an active radar seeker, mid-course data link, and a lethal endgame inside a robust no-escape envelope. Mark II stretches that envelope with a higher energy motor and refined guidance, so the zone in which a target cannot kinematically outturn the missile grows deeper and wider. Mark III changes the propulsion game with a sustained thrust solution, ramjet or throttleable ducted rocket class, keeping energy on tap throughout flight instead of expending it early. The practical result: more speed retained in the endgame, better ability to chase a target that turns cold, and a bigger bubble where evasive maneuvers don't work. Guidance and seekers evolve with the threat. An improved active radar seeker with better low side load performance and smart notch rejection keeps lock when targets try to hide in ground clutter or beam the radar. Home on jam logic turns enemy jamming into a cue rather than a shield. An inertial and GPS INS backbone steers cleanly during the mid-course phase, while a secure, high-update data link lets the launch aircraft or another network node refresh target vectors until the seeker goes terminal. Programmable fusing and aim point selection tune the fragment pattern for fighters, drones, or cruise missiles. Kinematics are only half the kill chain. The rest is geometry and timing. Mark II's higher impulse gives earlier shot opportunities against hot targets and holds energy longer against crossing shots. Mark III's sustained thrust lets Indian fighters take stern chase shots with confidence, maintaining missile Mach numbers deeper into the endgame where many BVRs slow down. That widens the tactical playbook. Bracket shots from two angles. A leading missile to force a break followed by a high-probability second shot, or a cooperative engage where one fighter provides mid-course updates while another remains radio silent. Survivability against countermeasures improves in layers. ECCM packages filter deceptive jamming and Doppler notches. Monopulse techniques resist angle noise. And seeker agility plus refined waveform libraries make it harder for digital radio frequency memory jammers to create convincing ghosts. In the terminal phase, high off-bore sight endgame agility and proportional navigation with late-stage energy management raise miss-distance discipline for reliable fragment overlap on fast jinking targets. Integration across IAF platforms turns Astra from a missile into a system. Su-30 MKI provides heavy carriage and cooperative targeting with a large radar. Tejas Mk1A brings agile cues from a compact AESA. Upgraded MiG-29 and Mirage fleets add mass to the network. Common pylons and weapon interface standards simplify fleet loading, while mission computers push pre-computed, no-escape envelopes to the pilot's display so shots are taken inside credible probabilities of kill, not marketing ranges. Captive carry, separation, and high AOA release envelopes allow safe shots across the flight envelope without compromising the launch aircraft. Doctrine shifts as range increases. A larger Mk2-3 no-escape zone means earlier sanitization of airspace, ahead of strike packages, and more comfortable standoff for AWACS and tankers under fighter cover. Against cruise missile raids or high-value ISR aircraft, the extended reach keeps threats further from Indian airspace and complicates their timelines. In mixed packages, Astra-armed escorts can hold enemy fighters at bay while strike aircraft focus on their targets, reducing the need to expend expensive standoff munitions defensively. Logistics and sovereignty are strategic multipliers. Indigenous seekers, propulsion sections, fuses, and data links reduce exposure to foreign supply shocks, allow rapid software refreshes as adversary tactics evolve, and create a sustainment pipeline matched to IAF sortie rhythms. Common canisters and test equipment across MKI-2 and 3 reduce ground crew workload and turnaround time on the line. Limits and honest counters remain. Low observable targets compress detection and track ranges. Saturated jamming environments demand clean, multi-platform queuing. And long-range shots always carry timeline risk if track quality decays. The answer is training and networks. Shoot inside solid track fidelity. Pair fighters with AEW&C support. And use cooperative mid-course updates, so end-game seekers arrive with minimal search. What changes for the pilot is confidence. With MK2 and especially a sustained thrust MK3, the IAF's first shot chance improves. Re-attack windows reopen faster, and enemy fighters must carry more fuel and accept more drag to hedge against long-range threats. Over time, that fatigue on adversary tactics is deterrence in its own right. For deep dives on Astra propulsion, seekers, and IAF BVR tactics in contested airspace, visit globalinfoveda.com. TED-BF takes shape, India's twin-engine deck fighter for carrier dominance. India's next big leap at sea won't be a ship, it will be the fighter that sails with it. The twin-engine deck-based fighter, TED-BF, is being designed to give Indian carriers a homegrown, high-end air wing built for rough seas, short runways, and long missions over water. Here's a clear tour of what TED-BF is, how it's engineered for carriers, and what it means for India's naval aviation in the 2030s. What TED-BF is solving. Carrier aviation needs more than raw performance. Fighters must launch off a ski jump, absorb hard deck landings, fold for cramped hangars, resist salt corrosion, and bring back unused weapons safely. India's current MiG-29K fleet does part of the job. TED-BF aims to replace it with a design optimized from day one for Indian carriers and missions in the Indian Ocean region. Airframe and carrier-proof design. Twin-engine canard delta layout for lift at low speeds and authority during high-alpha approaches. Reinforced landing gear, a arrestor hook, and a beefed-up spine to take repeated traps on a pitching deck. Folding outer wings and compact nose geometry to fit carrier lifts and dense hangar spots. Extensive marinization, anti-corrosion coatings, sealed avionics bays, and quick-swap line replaceable units for turnarounds between deck cycles. In-flight refueling probe and large internal fuel fraction to extend time on station without hogging deck cycles. Propulsion, launch, and recovery. 2 high-thrust afterburning turbofans in the 95 to 100 kilonewton class each, navalized, giving healthy thrust-to-weight for ski jump launches with meaningful bring-back loads. Stow bar, focus, ski jump takeoff, arrested recovery for INS Vikrant/INS Vikramaditya. Provisions and margins aim to be compatible with future Catabar operations if India fields a catapult-equipped carrier. A launch planning accounts for wind over deck, fuel, and weapon mass so sorties can launch heavy loads in cooler, night, morning windows and cycle lighter caps during hot afternoons. Avionics, sensors, and electronic warfare. Indigenous AESA radar navalized with maritime modes, sea search, periscope small target detection, and high-resolution SAR for coastline targeting. Passive sensor suite, IRST for long-range non-emitting detection and a 360 degrees missile approach warning system. Digital glass cockpit with sensor fusion so the pilot sees a single, decluttered picture, critical in salty, low-visibility decks. Full spectrum EW, digital RF memory jammers, towed decoy, and expendables tuned for shipborne threats. Weapons and mission sets, fleet air defense, Astra family BV rams plus high off-bore sight WVR missiles. Maritime strike, anti-ship missiles in the BrahMos NG/Next Gen class, and smart glide weapons for standoff littoral targets. CADED, anti-radiation missiles, Rudrum class, and programmable decoys to crack coastal sand belts. Precision strike, LGBs, SAAW-type munitions, and GPS INS glide bombs sized for ski jump launches and deck bring-back limits. Networked tactics with carrier AEW helicopters and shore-based AEW&C for composite air pictures over hundreds of miles. Carrier integration and deck rhythm. Designed around Indian deck geometry, spotting footprints, lift clearances, and tie-down points. Turnaround built for Temco, quick engine and systems checks, modular weapon loading, and hot pit refueling to meet tight launch recovery cycles. Data links to surface combatants and P-8I patrol aircraft so the fighter can queue ship missiles or receive target quality tracks from the fleet. Operational payoffs. Longer legs and heavier bringback than legacy jets mean fewer sorties to defend the carrier and more options in bad weather. Twin engines raise confidence over blue water. Canards and a big wing reduce approach speeds for safer traps. Indigenous supply chain and mission systems reduce foreign bottlenecks and allow faster software tactics updates. Development path and timelines. Big picture. It concept matured after carrier experience with MiG-29K. Wind tunnel and CFD work informed the Canard Delta and folding wing choices. A first flight and prototype test campaign paved the way for weapons separation trials, ski jump validation, arrested landing cycles ashore, and then at-sea trials. Entry into service targets the early mid-2030s, aligned with MiG-29K retirement windows and the need to field a majority indigenous air wing. Risks and what to watch. Weight creep versus bring-back margin. Naval fighters live or die by approach speeds and hook loads. AESA/EW integration in a salty environment. Reliability and maintainability must match performance. Engine growth path. Assured supply and future thrust upgrades keep launch margins healthy on hot decks. Okay, test tempo, arrested landing cycles, and sea trials take time. Schedule realism is a capability in itself. TED-BF is India's attempt to turn lessons from a decade of carrier flying into a purpose-built, sovereign deck fighter. The program holds its performance and reliability targets. Indian carriers in the 2030s gain a tougher combat air patrol, deeper maritime strike, and a truly Indian playbook for air power at sea. For deep dives on naval aviation, carrier operations, and India's homegrown combat systems, visit globalinfovita.com.
Coastal radar chain, P-8I, and maritime drones, a new eyes out strategy. Sea control begins with seeing first. India's eyes out strategy pushes surveillance away from ports and bases into the approaches where threats start, not where they finish. A national coastal radar chain stitches together island and mainland nodes for persistent horizon watch. Long-range P-8I patrol aircraft sweep deep water with powerful sensors. And maritime drones, fixed wing, rotary, and surface, fill the gaps with endurance and proximity. The result is a layered, distributed picture that turns the Indian Ocean's traffic from noise into knowledge and shortens the time from first contact to decision. Start at the shoreline. Chain-linked coastal surveillance radars sit on headlands, islands, and towers to extend line of sight along shipping lanes, straits, and fishing grounds. High-mast sites and island outposts raise the radar horizon, so even small, fast boats and low-profile craft that hug the surface appear in timed Q patrols. Each site feeds real-time tracks to regional hubs, where Automatic Identification System, AIS, data from commercial ships is fused with radar skin returns. When a vessel spoofs or switches off AIS, the skin track persists, flagging it for inspection. Passive receivers pick up maritime communications and navigation beacons, adding another layer for correlation without transmitting a pulse. Beyond the horizon, the P-8I is the long-range net. It's mechanically scanned surface search radar with synthetic aperture and inverse SAR modes maps. Ships and even shore infrastructure at high resolution, while a powerful electronic support suite listens silently for emitters, radars, data links, and radios. Magnetic anomaly detection and acoustic processors exploit patterns from sonobuoys to track submarines and choke points and patrol boxes. EO/IR turrets give visual ID when rules of engagement or fisheries enforcement require eyes on. With aerial refueling and high transit speed, a single aircraft can sweep a 1,000-mile arc, then loiter to build continuity on suspicious contacts. Drones complete the mesh by living where manned platforms cannot stay. Long-endurance fixed-wing UAVs trace racetrack orbits along sea lanes, feeding radar, EO/IR, and AIS sniffers into the same network as the coastal chain. Ship-launched rotary UAVs lift off from frigates and Coast Guard vessels to peek beyond the ship's radar horizon, vectoring boarding teams and providing overwatch for small boat encounters. Uncrewed surface vessels, USVs, loiter near straits or sensitive offshore assets as pickets, relaying contacts via low probability of intercept links. Because drones are cheaper to keep airborne, they fill time gaps between P8I sweeps and give persistence to targets of interest. Fusion turns many sensors into one truth. A maritime operations center ingests tracks from coastal radars, P8I sorties, drones, warships, and partner nations. Algorithms deduplicate, classify by behavior, speed, course changes, AIS anomalies, and promote contacts that deviate from expected patterns. Controllers push composite tracks back to patrol craft, aircraft, and coastal police via secure networks, so the unit nearest the contact has the same common operating picture as headquarters. The same fused picture feeds coastal missile batteries and air defense nodes. If a contact escalates from law enforcement to national defense, the handoff is instant. The payoff is speed and proportionality. A suspicious dark vessel detected by the radar chain is cross-checked by a drone for imagery. If risk rises, a P8I sweeps the sector and drops a pattern of sonobuoys to rule out a submarine partner. A Coast Guard ship closes in with live video from its rotary UAV. If the contact turns hostile, surface combatants and aircraft already have geometry, identifiers, and recorded behavior. Evidence that speeds decisions and clarifies rules of engagement. Islands multiply leverage. Outposts in the Andaman and Nicobar and Lakshadweep extend radar horizons and UAV basing far into busy straits and sea lanes. Pre-positioned fuel, hardened shelters, and quick-turn maintenance let drones surge during monsoon breaks or crises. Each island node acts as a relay and lily pad, reducing response times and widening the area under persistent watch without overstretching mainland squadrons. Electronic warfare and cyber resilience keep the picture honest. Emission control plans rotate radar modes and power, reducing predictability to hostile ELINT. Directional encrypted links connect drones and P8Is to shore, with fallback satellite paths when jamming bites. Data validation routines flag spoofed AIS or synthetic radar targets. Operators can pull raw sensor frames to verify. Red teaming and regular drills, turning sensors off and on, simulating outages, failing over to backups, ensure the network degrades gracefully rather than going dark. Counter-submarine vigilance is built into the fabric. Coastal arrays cue P8Is to lay sonobuoy fields across likely approaches. Surface ships use variable depth sonar to confirm. UAVs stand watch overhead for periscope wakes and mass signatures near shipping lanes. Even when no hostile submarine is present, the routine forces any covert intruder to assume detection and behave cautiously. Deterrence by process, not just by platform. Industry and sovereignty matter for staying power. Indigenous coastal radar production, domestic UAV airframes and mission systems, secure data links and software-defined fusion stacks reduce dependence on foreign pipelines and allow rapid updates as smuggling tactics and gray zone probes evolve. Standardized interfaces let new sensors and drones plug in without a bespoke integration project each time, keeping the network agile as threats change. The strategic effect is a wider, calmer moat. With the coast watched by a stitched radar chain, deep water patrolled by P8Is, and gaps filled by drones and ships on cooperative links, India moves from reacting at the shoreline to shaping behavior far out at sea. Fishermen, merchants, and navies operate under a predictable eye. Bad actors find their windows smaller and riskier. For deep dives on maritime domain awareness, sensor fusion, and India's evolving eyes-out posture, visit globalinfoveda.com.
Carrier Battle Group 2.0, Vikrant-led fleet and next-gen escorts. A modern carrier battle group is a moving piece of national territory, airfield, missile battery, sensor web, and command post in one. India's next iteration is a Vikrant-led fleet, where the carrier's air wing, next-gen escorts, submarines, and patrol aircraft operate as a single organism that sees first, shoots far, and survives contact in contested seas. This is the continuous story of how a Carrier Battle Group 2.0 comes together and what changes when INS Vikrant is at the center with newer escorts on her flanks. Start with the flight deck. Vikrant's stowbar layout launches fighters off a ski jump and recovers them by arrestor gear, giving the fleet round-the-clock combat air patrols, maritime strike sorties, and airborne scouting. The current air wing of MiG-29K KUB provides fleet air defense and anti-ship strike, while the deck cycles helicopters for anti-submarine warfare, logistics, and search and rescue. As the decade turns, the deck plan evolves. More capable AEW/ASUW helicopters, shipborne UAVs for persistent ISR, and a transition toward an indigenous deck fighter to extend reach and sortie endurance. The practical effect is a denser protective bubble and longer standoff for strikes without overtasking the deck. To port and starboard sit the group's fists and shields, next-gen destroyers and frigates. Visakhapatnam-class destroyers carry long-range air defense missiles on a bar-stretched, vertical launch farm, a phased-array radar that watches hundreds of miles of airspace, BrahMos for sea denial, and powerful electronic warfare suites. Nilgiri-class frigates add a second ring of air and surface defense with compact AESA, modern VLS, and quiet hulls optimized for anti-submarine work. Together, they create a layered dome, interceptors and jammers up high, guns and soft kill close in, so a raid must defeat multiple, overlapping systems before it ever sees the carrier. Under the surface, a silent screen moves ahead of the group. AIP submarines in the near term and nuclear-powered attack boats as they arrive, sanitize choke points, listen for opposing submarines, and sit astride likely ingress routes. Their presence forces any hunter to slow down and turn on active sonar, which in turn exposes them to the group's helicopters and patrol aircraft. The carrier does not sail alone. It sails with an underwater escort that sets the tempo for the fight you never see. Air and sea sensors fuse into one picture. MN Star-class arrays on destroyers, new AESAs on frigates, hull and towed sonars, helicopter dipping sonars, and UAV ISR feeds all flow into a combat management network that shares tracks across the group. Cooperative engagement logic matters. A missile can be fired by one ship using targeting from another, or a fighter can take a beyond visual range shot, guided by a destroyer's radar track. This breaks the old idea of local bubbles and turns the group into a distributed weapon system, where any sensor can cue any shooter. Strike reach grows without dragging the carrier into danger. Fighters armed with BVRAAMs and anti-ship missiles extend the outer air battle, while escorts hold heavy standoff rounds for surface targets. Land attack options from surface combatants add pressure on shore radars, SAM sites, and logistics nodes. The rule is economy. Keep the carrier at the edge of threat rings while long-reach weapons and scouting assets do the risky work forward. Survivability is doctrine as much as steel. Emission control keeps the group hard to find. Decoys and electronic attack complicate enemy targeting. Maneuvers exploit weather and sea clutter. And disciplined magazine management ensures the right mix of interceptors, decoys, and strike rounds is always on tap. Damage control drills, redundant power and combat systems, and armored, shock-mounted vital spaces buy time when a hit lands. The aim is graceful degradation, fight hurt, reconfigure, and keep the air plan running. Logistics and rhythm make power sustainable. A replenishment ship shuttles fuel, aviation stores, and missiles so the group can persist far from home ports. Turnaround on deck is measured in minutes. Hot pit refueling, quick weapon swaps, and predictive maintenance keep sortie rates high. The escorts cycle helicopters in ASW barriers, while UAVs maintain continuous maritime domain awareness. When the air plan, the missile plan, and the fuel plan align, a group holds sea room for as long as policy demands. Training turns capabilities into choreography. Composite training with maritime patrol aircraft extends the group's eyes. Coastal radars and satellites add cueing for far sea intercepts. Joint drills rehearse contested EM spectrums where jamming, decoys, and cyber disruption are expected. The measure of readiness is not a parade of platforms, but the ability to retask in minutes when a contact appears where it shouldn't. The strategic payoff is flexibility. A Vikrant-led CBG with next-gen escorts can escort convoys, cover amphibious moves, keep sea lanes open, and impose costs on any fleet that approaches Indian shores. It signals presence in peacetime, offers calibrated coercion in crisis, and brings a mobile, sovereign airbase to any part of the ocean where national interests are at stake, all while staying within a layered shield that travels with it. For deep dives on carrier operations, next-gen escorts, and the future of India's sea control, visit globalinfoveta.com.
Indigenous SSN program, nuclear attack submarines for sea control. Sea control is a contest of endurance, reach, and silence, and nothing combines those like a nuclear-powered attack submarine. India's indigenous SSN program aims to field boats that can sprint to a crisis, linger for weeks without snorkeling, and hold hostile surface groups, submarines, and shore targets at risk across the Indian Ocean and beyond. Here we explain what an Indian SSN must be, how it fights, and why it reshapes the Navy's options for the next 3 decades. Start with the physics that matter. A nuclear reactor turns seawater into steam, and steam into motion without the oxygen limits that bind diesel-electric designs. That gives an SSN practical endurance measured in months, limited mainly by food and crew stamina. It also gives sustained speed, not just a brief dash, but the ability to run quietly at higher transit and patrol speeds, collapsing the time from order to on station and expanding the radius the boat can cover in a single deployment. Endurance and speed together are deterrents. They let commanders appear where an adversary expects safety. Silence remains the currency of survival. Quieting starts with a compact, well-shielded reactor, double or rafted machinery mounts, and a propulsion train tuned to avoid resonances. A pump jet or carefully shrouded skew-back propeller reduces cavitation at speed. Anechoic tiles and careful hull shaping scatter active sonar energy. Isolation of auxiliaries, pumps, compressors, turbines, keeps the acoustic profile low across bands. Every cable run and pipe bracket is a choice about noise. Every choice adds up to how close the boat can approach before detection. Sensors and combat systems turn silence into leverage. A spherical or large bow array, long flank arrays, and a towed passive array together provide the aperture needed to detect faint contacts at range. Wideband receivers harvest radar and communications emissions to build an electromagnetic picture without ever raising a mast. When the boat must look, a low-profile optronic mast with high-definition, low-light optics compresses periscope time to seconds. A modern combat management system fuses all of this into a single prioritized track picture, so a small crew can classify, target, and engage without cognitive overload. Weapons define the dilemmas the SSN sets for an adversary. Heavyweight torpedoes remain the close and kill mechanism against surface ships and submarines, with wire guidance allowing patient, precise shots from ambush geometry. Vertical or encapsulated launch options for cruise missiles extend reach to enemy surface task groups and, where policy authorizes, shore targets such as logistics nodes, air defense sites, and radar stations. Encapsulated anti-ship missiles fired from torpedo tubes add punch in contested littorals. Decoys and mobile emitters seed confusion in an enemy's sonar picture when it is time to break contact. Missions span the spectrum of sea control. In choke points, an SSN can act as a gatekeeper, denying hostile submarines and surface combatants access to the open ocean. Along sea lines of communication, it can shadow and, if necessary, attrite adversary strike assets that threaten merchant traffic. As a carrier escort, it clears the underwater approaches, hunts opposing submarines, and extends the carrier group's sensor net far forward. In wartime, it can break blockades, sever logistics, and interdict high-value units. In peacetime, it conducts intelligence, surveillance, and reconnaissance, listening to seabed signatures, mapping routes, and validating tactics against real targets. Operations are a choreography with the wider fleet. Maritime patrol aircraft queue with sonobuoys and magnetic anomaly detections. Surface combatants fence at standoff. Satellites and seabed sensors feed context. And the SSN shares only sparse burst data on low probability of intercept links to preserve location secrecy. The art is timing. Arrive early, settle into favorable acoustics, wait for patterns, and strike or shadow when the odds are best. With nuclear endurance, the boat dictates the calendar instead of being driven by batteries. Industrial choices decide whether the promise becomes presence. A domestically designed reactor with reliable, safe control systems must be compact enough for a hydrodynamically clean hull. Quiet main coolant pumps or natural circulation regimes at low power cut tonal noise. Indigenous supply of high-strength steels, quiet bearings, cables, valves, and shock-mounted auxiliaries turns availability from a procurement question into a manufacturing discipline. Yard infrastructure, covered building halls, nuclear-qualified dry docks, radiological protection, and specialized test facilities, sets the tempo for construction, refueling, and deep maintenance over a 30-year life. People and procedures are as critical as metal. Crews need long pipelines for nuclear engineering, reactor watch, acoustic analysis, damage control, and under-ice or shallow water navigation techniques tailored to the Indian Ocean's thermoclines and seabed. Shore organizations must institutionalize strict reactor safety, radiological monitoring, and incident response that withstand scrutiny. Tactics schools must iterate playbooks continuously as foreign sonars, torpedoes, and patrol methods evolve. Counter capabilities will improve, so doctrine must be honest. Adversaries are fielding low-frequency active and multi-static sonars, improved airborne processors, satellite-aided ocean surveillance, and smarter torpedoes. An Indian SSN answers with speed to reposition outside detection cones, disciplined speed control to stay below acoustic layers, deceptive countermeasures, and the patience to use noisy seabeds and shipping as cover. The goal is not invulnerability. It is an unfavorable cost curve for any hunter. Strategy is where the investment pays out. A handful of SSNs on rotation across key approaches, from the Arabian Sea and Mozambique Channel to the Andaman Sea, forces any adversary to protect convoys with scarce escorts, slows task forces, and opens windows for air and surface forces to shape outcomes. They also protect India's own SSBN bastions, ensuring the credibility of the nuclear deterrent by hunting threats before they reach missile boats. In crises short of war, the knowledge that a quiet, fast, long-legged submarine may be watching alters calculations without a press release. Timelines and risk are real. Designing, building, and sustaining SSNs demand long lead times, tight program discipline, and unglamorous investments in training and infrastructure. But the payoff is a sovereign tool of sea control that does not depend on access to foreign ports, airspace, or tankers. An indigenous SSN program, done right, is less a platform purchase than a national capability that compounds over decades. For deeper analysis on undersea warfare, nuclear propulsion, and India's path to credible sea control, visit globalinfoveda.com.
Zorawar Light Tank, high-altitude armor for mountain warfare. Mountain warfare punishes heavy steel and thin air. India's Zorawar light tank is being shaped for that environment. Built to move fast on narrow roads and broken tracks, fight from steep angles, and survive in cold, high-altitude valleys where main battle tanks struggle. This is a deeper case study of what a modern Indian light tank must do in the Himalayas and why Zorawar changes the calculus along the line of actual control. The starting point is mobility. A weight class tuned for bridges and mountain tracks lets Zorawar reach places a 60 to 70-ton NBT cannot, with ground pressure low enough for snow, scree, and wet meadows. A turbocharged power pack with high-altitude calibration offsets thin air, Multi-stage filtration handles dust in summer and snow fines in winter. An auxiliary power unit supports silent watch without idling, and a cold start tackage, fuel heaters, battery warmers. Low-temperature lubricants keeps the tank reliable at -30 degrees Celsius. Rubberized or segmented tracks reduce vibration and road damage, while a compact hull and tight turning radius matter on hairpins where one bad pivot can block a brigade column. Firepower is about angles as much as caliber. A 105 to 120 millimeter high-pressure gun with generous elevation and depression handles ridge-to-valley shots and reverse slopes. A modern fire control system stabilizes over broken ground, fuses laser range, meteorological data, and inertial cues, and enables hunter-killer commander-gunner handoffs for rapid target servicing. Ammunition families include APF-SDS for armor threats, Heat MPAT for bunkers and light armor, and programmable airburst HE to clear defilades, drones, and infantry behind rocks or walls. A coaxial gun and a roof remote weapon station give close-in overwatch without exposing crew. Gun-launched ATGMs or external canisters add standoff when a narrow valley becomes a missile alley. Protection trades smartly for weight. A welded base hull with modular composite add-on armor allows threat-based kits, lighter for rapid marches, heavier for key sectors. Spall liners, energy-absorbing seats, and separated fuel improve crew survival. A hard-kill active protection system intercepts top attack and direct attack threats. A soft-kill suite jams seeds decoys against laser and IR-guided munitions. 360 degrees EO cameras and acoustic shot detectors feed a panoramic display so the crew sees climbers, quads, or AT teams on spurs before the first shot. NBC sealing and overpressure are standard for high-altitude chemical decontamination constraints. Sensors and networks make the tank a node, not a loner. A mastable sight or tethered micro-UAV extends line of sight over ridges. Blue force tracking ties Zorawar to infantry, mortars, and artillery. Targeting data flows to loitering munitions and rocket batteries for combined fires. Counter-UAS tools, RF detectors, programmable airburst, and a compact jammer protect against quadcopters cueing enemy guns. Terrain and route data load into the battle management system so crews pre-plan hull downs, bypasses, and recovery sites before first light. Survivability in mountains is position and procedure. Zorawar fights from hull-down scrapes and rock revetments, uses short pop-up shoot-scoot cycles to avoid counter-battery, and employs deception, thermal blankets, false tracks, inflatable decoys to dilute enemy ISR. Smoke with multispectral properties hides against EO/IR, and a quick erect dozer blade can throw a berm in minutes. Recovery kits and winch points are standardized because a broken track on a cornice is a platoon problem, not a crew problem. Logistics decides tempo. Modular LRU design lets techs swap packs and sites at altitude with minimal tools. Pre-positioned spares, fuel pods, and ammo caches sit at roadheads. 4x4, 6x6 support vehicles move in leapfrog to keep platoons wet and fed. Air portability by C-17 and sling-loadable sub-kits by heavy-lift helos for select components accelerates theatering, while rail-to-road interfaces shorten build-up times from planes to passes. Winterization checklists, coolant mixes, track tension for snow, battery care are drilled like gunnery. Doctrine adapts to heights. Light tanks pair with mountain infantry and sappers in company teams. Infantry clears spurs and AT nests. Engineers cut laybys and snow cuts. Zorawar provides direct fire, mobile cover, and shock. In valleys, platoons bound by fire from spur to spur. On plateaus, they anchor mobile screens that deny enemy patrols freedom of movement and hold key junctions for artillery to exploit. In crises, speed to key bridges, saddles. And airfields is the deterrent, a visible, credible gun on the right spur at the right hour. Why it matters is strategic and practical. A light, networked, protected gun platform restores maneuver to the mountains, reduces reliance on scarce MBT-compatible routes, and multiplies the effect of drones and rockets by forcing the enemy to respect direct fire threat at altitude. Done right, Zorawar gives commanders a tool that shows up where maps say impracticable, buys time for heavier forces and holds ground that decides negotiations after the shooting stops. For deep dives on mountain armor, active protection, and India's evolving high-altitude warfare toolkit, visit globalinfoveda.com.
Project 75I AIP submarines in the next wave of undersea deterrence. India's next leap underwater will be quiet rather than flashy, and that is the point. Project 75I aims to field a new class of conventional submarines with air-independent propulsion, AIP, giving the Navy the endurance and stealth to hold sea lanes, shadow adversaries, and complicate any planner's map of the Indian Ocean. This is the continuous story of why AIP matters, what a 75I boat must do from keel to combat system, and how it reshapes deterrence in the 2030s. Start with the physics of stealth. A conventional submarine is at its most invisible when the diesel engines are off and the boat runs on batteries. Traditionally, that quiet window lasted hours to a couple of days before snorkeling to recharge, an act that raises a mast, emits heat and noise, and invites detection by radar, infrared, or electronic surveillance. AIP inserts a second, much longer quiet window. Whether using fuel cell stacks that combine hydrogen and oxygen to produce electricity, or closed-cycle Stirling engines that burn fuel with stored oxygen, AIP lets the boat stay submerged for a week or more at slow patrol speeds without snorkeling. The payoff is operational, not just technical. Patrol boxes get wider, ambush positions last longer, and commanders can wait rather than rush. A 75I hull must be drawn around that mission. The design balances displacement for fuel, oxidizer, and batteries with the hydrodynamics that keep flow noise low. Rafted machinery mounts, anechoic tiles, and careful propulsor shaping suppress the acoustic signature. Double hull or partial double hull choices trade damage tolerance against weight. Every penetrator, mass, towed arrays, weapon tubes, is a potential noise source, so routing and isolation matter as much as raw power. Inside, a combat management system fuses inputs from flank arrays, a bow sonar, towed passive arrays, intercept receivers, and optronic masts into a single prioritized picture that a small crew can fight without cognitive overload. Weapons and sensors set the submarine's leverage. Heavyweight torpedoes remain the close-in punch. Wire-guided shots from quiet, pre-planned positions deny surface combatants freedom near choke points. Anti-ship cruise missiles launched from torpedo tubes or vertical modules turn the boat into a sea denial sniper, able to threaten high-value units from standoff range. Land attack options, if integrated, extend deterrence ashore against logistics nodes, radar sites, or coastal batteries. A modern electronic support suite listens for radar and communications emissions, building an electromagnetic picture that guides ambush geometry without revealing the boat. Periscope moments must be rare and short. High-definition, low-light optronics and periscopeless masts help compress the exposure. AIP choice drives the engineering rhythm. Fuel cell systems offer very low acoustic and thermal signatures with high electrical efficiency, but they demand robust oxygen storage, careful hydrogen logistics, reformer-based or pre-stored, and rigorous safety engineering. Stirling solutions are mechanically simpler and proven at sea, though their moving parts and exhaust management raise different integration questions. In both cases, the real art is hotel load discipline, smart power management that lets sonar arrays, combat systems, and life support sip rather than gulp. Lithium-ion batteries, if adopted, boost sprint and recharge profiles, but require advanced thermal management and fire safety. Tactics change with endurance. Instead of sprint drift patterns driven by battery anxiety, 75I boats can take slow, patient positions across straits, sea lanes, and submarine approaches to carrier groups. They can shadow quietly for days, queuing maritime patrol aircraft or surface forces via burst transmissions on low probability of intercept links. In a crisis, the mere uncertainty about where an AIP boat sits forces an adversary to widen escorts, slow convoys, and devote scarce anti-submarine assets to protection rather than offense. Deterrence is purchased in planning hours. The opponent's staff must assume a stealthy presence, and that assumption shapes cautious behavior. Industrial choices are strategic choices. Project 75I is not just a buy, it is a build. With transfer of technology and domestic production of hull sections, combat systems, integration, and lifecycle support. Indigenous content in sonars, periscope heads, batteries, fire control software, and weapon interfaces reduces external bottlenecks and allows faster tactics software updates after fleet exercises. A well-designed through-life support model, spares pipelines, dockyard skills, and AIP module overhauls decides availability as much as the launch date. Survivability is more than silence. Shock hardening for weapons hits, redundant pumps and chilled water loops, fire detection and suppression in battery compartments, and rigorous damage control training keep a boat in the fight after the first bad minute. Navigation suites with under ice or shallow water modes, mine avoidance sonar, and precise inertial systems reduce peacetime risks that have ended many submarines' careers far from combat. Integration with the wider fleet turns stealth into strategy. A 75i boat does not hunt alone, it's a node. Maritime patrol aircraft seed sonobuoys to herd targets. Surface ships hold at standoff while the submarine scouts. Satellites and seabed sensors contribute cues, and data moves sparingly across secure burst links to preserve location secrecy. Exercises that practice this choreography, silent queuing, timed missile launches, and handoffs to air or surface shooters, turn potential into repeatable effect. Risks encounters deserve honesty. Modern adversaries field low-frequency active sonars, multi-static networks, magnetic anomaly detectors, and satellite-aided surveillance of wakes and thermal signatures. AIP endurance narrows detection windows but does not erase them. The answer is disciplined speed control, clever bottoming tactics on noisy seabeds, deceptive decoys, and relentless acoustic hygiene. Training makes the difference between a quiet design and a quiet patrol. The strategic picture is straightforward. A handful of AIP submarines on rotation across choke points, from the Arabian Sea approaches to the Malacca-bound routes, can complicate any hostile task force and secure India's own sea lines in a crisis. They buy time for carriers and air power to posture, they hedge against surprise, and they give political leaders credible options short of overt escalation. Project 75i, if executed with sober engineering and strong sustainment, is less about prestige and more about pressure. The quiet kind that shapes choices without shouting. For deep dives on undersea warfare, AIP technologies, and India's evolving maritime deterrence, visit globalinfoveda.com.